So a quick review, something that I wanted to mention was atoms that are isoelectric and how we can notate that. So these would be atoms or ions with the same number of electrons, which is another way of saying they have the same electron configuration. Okay, so iso means same, and then electric, number of electrons. So for example, we could look at neon. Neon has is 1s2, 2s2, 2p6. And so if we look here at neon, so here is neon. Now, if I give an extra electron to fluorine, that's isoelectric with neon. So if I have F minus, that would also have the same electron configuration as neon. So I could either just write same electron configuration as neon, or I could do 1s2, 2s2, 2p6. Okay. I can also go one more and say give oxygen 2 electrons. So I can have O2 minus. And that's going to have the same electron configuration as neon. Now I can go the other way. I can remove an electron. And so if I remove an electron, then I can become, so if I have neon and I get rid of an electron, so I can go and be like sodium. So then, or if sodium loses an electron is how I should say that. So sodium loses an electron, it looks like neon, right? So sodium right here, if it loses an electron, it goes back to neon. Magnesium loses 2 electrons, same thing. So we have Mg2+. That's also isoelectric with neon. So we would say in this particular situation that Na plus, Mg2 plus, F minus, O2 minus are isoelectric with neon. Okay, that's just a little reminder about that. Okay, and then we move on to ionization energy. So ionization energy is the next big trend. And as the name implies, we're going to be looking at the energy required to ionize an atom. And it could be an ion as well, because there's different ionization energy numbers. So ionization energy we abbreviate as IE. And we'll use a subscript for the number of electrons removed from the parent atom or number of ionization energies. So why we care about ionization energies is that the stability of outermost electron, which we again call a valence electron, is related to an atom's ionization energy. Now we tend to look at the first ionization energy the most, but I'll give you a couple situations where it's helpful to know how it goes for multiple ionizations. So to define ionization energy, it is the minimum energy required to remove an electron from a gaseous atom in its ground state. So let's just do an example of that to kind of understand what it means. So let's say we have like carbon, for example. Carbon has 1s, it's got 2s, and then if we look at carbon, come up here, carbon is, so it's got 1s, 2s, and then 2p2. So 1s, 2s, 2p, 1, 2. So the first ionization energy, IE1, is going to look to remove this electron. So the ground state means that we don't have an electron up in a 3s orbital or higher. So that this electron is in the lowest energy state. It's harder to remove an electron when it's in this lowest energy state. You would assume it would be take less energy if it's in an excited state. It's farther away from the nucleus, less attraction. So that's the first ionization energy. The second ionization energy would be to remove the second outermost electron, which in this case would also be in the p orbital. So that's what it means. And then the gaseous state just means that we assume that there's no intermolecular interactions. So we don't have carbons bonded together. We don't have any type of interaction that would make this electron easier or harder to remove. Gases that are assumed to be far enough apart where they don't have any interaction. Okay, so if we write this out in an equation, we can see that, let's just say we have x. Again, there is no x elements, so we're just going to use that, and we're going to say we're going to add in some energy. This is going to be our ionization energy we're going to add. And we're going to ionize x to x plus an electron, and that's the first ionization energy. Now, if we take that x plus and we add more energy to it, then we get x2 plus the electron we removed, and that is the second ionization energy. And then we could go on to x2 plus energy down the line to get a further ionized ion. Now, we would expect that as we remove electrons, it's going to be harder and harder to remove an electron because you have the same number of protons, but you have less electrons repelling each other, and so we would expect that those electrons are being held closer to the nucleus. They are being bonded or bound to the nucleus with a tighter attractive force. So the first ionization energy is going to be lower than the second, so it gets harder and harder to remove ionization energies as you continue down. And we can see that with that p-table app as well. So successive ionization energies continue to increase. And so just to write out y again, so the Z effective is constant, meaning that the amount of shielding does not change, but the repulsion of electrons decreases with each successive ionization energy. So another point is that ionization energies are always positive. And the reason why is because whenever we remove, so an electron removal is always destabilizing, meaning that when a proton and electron are attracted to one another, that is always a stabilizing interaction. And so to remove an electron is to break that attractive interaction. That will always require the input of energy. So all ionization energies, even if something like sodium plus or sodium going to sodium plus, we know that it is going to gain a noble gas electron configuration, which we know is stable, but it still takes energy. It's still destabilizing to take away that electron because that electron is bound to the nucleus, is an attractive interaction. Okay, so that's the first thing. All ionization energies are positive. They trend, so with Z effective. So this kind of makes sense that it's harder to remove electrons that have a stronger attraction to the nucleus, which can be measured by the effective nuclear charge. So, or the pull at which the electron feels. So the greater the effective nuclear charge, Z effective, the greater the ionization energy. That's one. We know that noble gases have highest ionization energy 1, or the first ionization energy. And the reason that is because if we look at noble gases, if I want to remove an electron from krypton to get to bromine, then that would mean that I would lose my noble gas configuration, and that is definitely destabilizing. So whenever you have a noble gas configuration, the ionization energy to remove that electron is always very large. Okay, so that is to say that noble gases have a very stable ground state. All right. We also know that group 1 metals, like sodium, that we just talked about, have lowest ionization energy, have the lowest ionization energies, or the first ionization energy. And that again has to be because we have so these have the lowest Z effective for their row, and that's 1, and they also gain noble gas electron configuration for the first ionization energy. Remove an electron, and you get a pretty stable state. Now, it's still positive, remember, but it is very stabilizing. Okay.